All right, torque. Torque is given a funky letter. It looks like a T, but what you're going to do is you're going to draw a squiggly crossbar up top, and then you're going to draw almost like a backwards J, but it's actually more like a T. And it's just like a T, but the hook goes the other way if you're looking at a cursive T. And this is a Greek letter, tau, and it's a measurement. Torque is a measurement of rotational force. So we're talking about torque, rotational force. So specifically, torque measures how much a force acting on an object causes that object to rotate. And the equation for it will then be torque equals the radius times the force times sine theta. And just to reiterate, this letter that we're writing is, I think it's an uppercase tau. It's been a while. But we say tau. If you ever see it spelt out, that's how tau is spelt out. Just kind of like how T would be T-E-E when you write it out. Or if you're British, it might be T-E-A. Who knows? That's a joke. Because British people drink tea. Okay. Okay, anyways. RF sine theta. The other ways that this is written, tau could equal RF, that is perpendicular to it. And that's what matters, is the fact that it's perpendicular to it. And how else do you see that? Because what function did we use? Sine theta. So it's the amount that crosses. And because it's the amount that crosses, we also would say that tau equals radius crossing the force, which is very different than what we've seen before. Radius is a measure of what base units does radius have? What SI units? Meters? And then force is newtons. We've had something else with newtons and meters together. Do you remember what it was? Force times distance is work. And so if work is force times distance, that would be force dot distance. So it's a dot multiplication instead of a cross multiplication. And so physicists will sometimes use different multiplying signs just purely to denote that there's a difference between the two. That this would be the sign, right? Because work was force times distance cosine theta. So it's the force that was parallel to the distance, whereas this is the force that is perpendicular. And so that's what that cross multiplication means compared to the dot multiplication, I think. I could be just making that up right now. Who knows? You should look into it. The object rotates about an axis that we're going to call the pivot point. And the pivot point, P, is like the door hinge or whatever. We can apply a force, and we have the radius. The theta is the angle between our radial vector and our force vector. Okay? So the distance that we are away from the pivot point by the force direction. A lot of times the easiest way to look at that is end to end. So, P. No, sorry, this is R. R is the distance from the pivot point where the force acts. So it's also called the lever arm. Or the moment arm. Force applied. What's the letter? F. And it's measured in what units? How do you measure angles in geometry? Pre-cal. What symbol? Theta. Okay. Formed between what two things are even in this equation? R and F. So the force in the lever arm, right? The only components of force acting, only the components of force acting perpendicular. What function is inside of our equation? Sine. And so units, let me put sine theta right there. So units for torque is going to be Newton meter in M. And because it's torque, it's not work, it's not energy. We're not going to combine that to be joules, okay? Only work is joules. This is Newton meters. The direction for torque is either CW. What do you think that is? Or CCW is counter. And if I were to worry about convention, it would be like math class. So when we rotate through our quadrants, which way is positive? Counterclockwise is positive. So CCW, find CCW is positive. I skipped a blank to do that. I'm going to go back. CW then is negative. CW is positive. So it's negative then positive if you're going in order, filling in the blanks. The net torque is the... What do you think of when I say net torque? What are you doing? Addition. So it's the sum of individual torques. If ever I was using my English skills to communicate multiplication, I probably wouldn't say net or sum. I would probably say to multiply. What would I say? Product. Okay. Okay. If I wanted you to divide, I'd probably say ratio or fraction or something like that. All right. And so when a cyclist is pedaling, they would push, and honestly, this is when you have the optimal push and travel through to help propel your bicycle forward. If you have a pedal and your pedal is bottom and in the background it's top, and you're only pushing straight down, does it help you move forward? No. You kind of have to angle your pedal forward and push it forward to get any motion. And then a lot of people like that ride down is kind of comfortable when you stand on your bicycle pedals or something like that. It helps propel you forward. Does that kind of make sense? Bicycle riders know what I'm talking about. If you've never ridden a bicycle, that's okay. It's just it's hard to talk about rotation when you don't have the same experiences as us. I get it. What you do need to know is that what's the equation? Torque equals radius times force times sine theta. Good. All right. And so we're going to plug things in for all of these problems for the samples right below. That's what we're going to be using. I'm going to pause the video really quickly. We're going to play around and figure out how torque works best using an in-class example. These questions, however, deal with the angle at which we're at as we go through the bicycle push, RF sine theta. So the radius, the cyclist pushes downward 65 newtons. Pedals her bicycle as illustrated. Find the torque for each position if the radius is 16.5 centimeters. So what's the radius? 0.165. Good. What's the force? 65 newtons. And sine of, what's the angle? 90. Sine 90. That's just one. All right. What did you get? 10 point what? That sounds right. What else do I need to do? Newtons. What else do I need to do? Meters. What else do I need to do? I mean, of course it's down. The force is downward, but the radius is this way. So I'm going to say clockwise. I just wrote CW. Yeah, I only had enough space saved for CW. Guys, even though we could treat it as a vector with direction, it really isn't. It's a pseudo vector. assign it its direction as clockwise or counterclockwise. And conventionally, we just treat clockwise as negative and counterclockwise as positive. So if I wanted to rewrite this, I could say negative 10.725 Newton meters. Understanding convention. Oh no. Alrighty. Next one, torque equals radius times force times sine theta. If ever I say force times radius sine theta, is just the direction that I learned it in. Sometimes I'll flip-flop F and R. What are we going to do here? Plug it in. Same numbers. 0.165, 65, sine of, oh, this angle's changed, sine of 45. They always give us a reference angle as far as our force having slid over there, translated over there, so that we can see if they both start from the origin, what is the angle between the two? The lever arm vector versus the force vector, arrows. I would do the same is what I'm trying to hint at. Okay, sine 45. Sine 45. What'd you get? 7.58. 7.58 Newton meters clockwise. Good. That's all our little bits and stuff. Sine of 0 is 0. So when I do RF sine 0 equals 0. Alrighty, so we ended up with 0 for this one. 0 Newton meters, 0 foot-pounds, 0 whatever units we have. And we're going not clockwise, not counterclockwise, because 0 is 0. Doesn't even matter what units we pick, as long as they're torque units. What about this one? The angle's here. It's as if we moved this force right here. So same thing, 0.165 times 65 sine 60. 9 point what? 288. Counterclockwise, yes. Newton meters counterclockwise. Alrighty. Okay, so I've noticed that some students will review this notes and then they automatically think that the net torque equals 0 Newton meters. When you review this tonight or tomorrow night or right before the test is when sometimes y'all will ask these questions. What's the topic right here? Rotational equilibrium, which means we're not speeding up its rotation or slowing down its rotation. A lot of your rotation and equilibrium problems, things are just not rotating. Okay? So for an object to not rotate, sometimes though it's rotating at a constant speed. That's the other possibility. It's like that with forces, right? F equals ma, but when is your acceleration 0? Does that mean you're at a standstill? Sometimes you could be just sliding at a constant velocity. Same thing here. This occurs when the torque counterclockwise, all of the torques added together clockwise equals the counterclockwise. So CW equals CCW. You could have switched those around and it's okay. I think I said counterclockwise to start. It can be assumed that the entire weight force of an object is at the... There's 3 words. Center of mass. We'll see what I mean when I get to that problem later. All right, so this is for rotational equilibrium. We're going to set our net torque to 0, which means our torque counterclockwise subcategory equals our net torque clockwise and vice versa. Because they add to 0, right? If I were to add these two together, it adds up to 0 if I took into account their direction. So find the force needed to balance the seesaw. Ignore the mass of the seesaw. The net torque equals 0, which allows us to say net torque CW equals net torque CCW. Now, if I already have them labeled like that, that means I get to ignore the signs, right? Because I'm just going to say, hey, look, this side down is balanced out by this side down. We don't need to worry about, hey, this side is actually negative and this side's positive. If you were to use your base equation and say the net torque equals 0 equals force times radius vector-wise plus force times radius, one of those would be negative, and that's why we move it to the other side. At this point, we're just going to say force times radius equals force times radius. And if you're like Mr. Kwan, I thought it was radius times force. That's the same thing, okay? I just learned it force times radius. Don't freak out. I have 5 times 3 equals F times 10. 15 times 1/10 equals F. And yeah, simplifying it, you get 1.5. 1.5 what? Newtons. And of course the direction is down, but look at your picture. Do we need to describe the direction? No, it's already there. Yeah. All right, number 2. Find the force needed to maintain rotational equilibrium. Disregard the mass of the plank. Okay, so my net torque equals 0. And therefore, the torque clockwise equals the sum of the torque counterclockwise. What's going counterclockwise? What's going clockwise? Okay, so 4 times 60. Wait, that's a radius times a force. I'm going to need the other radius times the force then. What's the radius of the other one? The radius? No. 16. Yeah, you're right, 16. I heard 60. Now that you say 16 clearly, I'm like, oh yeah, you must have been saying 16. 16 and then what? F. So 4 divided by 16 is 1/4, and 1/4 of 60 is 15. What? Newtons. Good. Alrighty. My work is very similar or the same. Sometimes they'll throw in a third weight, but none of these have a third mass in there or a third weight in there. This kid is radius times force equals radius times force. That's because the net torque is 0. What are we going to say? 500 times 2 equals 4 times the weight that we're looking for. $1,000 divided by 4 is 250. What units? Okay, we know it's down. RF equals RF. What do we do here? 4 times 300, and that should equal R times 400, and then we solve for R. This is easy. Some of you mental math people already have it figured out. Cross out 0, cross out zeros. Those cancel. Then my 4's cancel. I'm left with R equals 3 meters. Clockwise, counterclockwise, directionless. It's in the picture. It's just the distance. Lever arm distance. Hard one. RF equals RF. I guess the harder ones would have 3 points. What is supplying our counterclockwise? Counterclockwise are positive values. One times 600. Is that what you're saying? 600 times 1. Okay. How far are we when we measure our center of the board? Yeah, the board. Only 3 meters away. The center is 3 meters away. Why am I using the 3 meters for the center of the board here? Okay, so yes, by definition, that's the board center mass. Why am I using the board center mass? It doesn't really make sense to use the end, right? The board's mass is distributed all along here. Am I allowed to use the average mass? Bullet point 3 says it can be assumed that the entire weight force of an object is at the center of mass for an object. So, what do we have here? We're solving for a force. 600 divided by 3 is newtons. Alrighty, the rest is yours. I've got a short video for you as well.